All right. I think we have two more talks. I'm just driving the slides. I'm not presenting. Ruth is one of my colleagues at Intel. She's a software architect. She's going to cover the Runtime RAS proof of concept work that has been done on the Coreboot with Intel FSP. And this is essentially a concept as a building block on what we want to do going forward. Ruth, can you hear us?
Hello, Randy. Thanks.
All right, go ahead.
Thanks, Randy. And thanks everybody to join this session. Randy, so now we are in page 3, right? Okay. Yeah. In this session, I do want to share what Intel has been doing in using FSP binary to supporting a different boot framework and the initiative of open system firmware. I will describe our technical solution on how we enable the runtime RAS with the Coreboot framework. The basic flow for this talk will include a quick brief about the open system firmware and FSP definition, and also make analysis about the problem we meet for enabling the SM drivers and providing by our solution on how to enable that. And also a quick close it with a quick demo to showcase our prototype work for the RAS enabling. Next page, please, Randy. Yeah. So in the left side, we all know that Intel has been play with open source ADK2 for many years. We host our ADK2 implementation and our open board reference implementation in TNO core. And to work with this open source component, we have multiple redistributable binary. And today I will mostly focusing on the FSP binary. The FSP binary will work with a different bootloader, including the Coreboot. I will touch mostly in today's topic. This year, we published the latest FSP spec 2.3. Let's take a quick look about how the FSP was generated. Normally, when we start a new silicon or new platform, we will implement a lot routines which to do these silicon initialization. And these modules is normally implemented in the closed source format. If we, in the FSP concept, we encapsulated these silicon initialization modules into FSP binary. And with this binary, it can be integrated to different bootloader. If we look into the FSP binary and think about how it to interact with the bootloader, we will see in FSP spec, we do define a set of standard interface, which can be called by the bootloader. In this picture, you will see multiple standard interface well documented in the spec. And after the bootloader calling into this interface, the silicon initialization modules existed inside the FSP binary, got invoked and finished the required routine. And on demand, it will providing some hub structure to let the bootloader know some very important information like the memory. In this way, the FSP binary will be easily integrated to different bootloader. Right now, the blue circled modules was already included in the FSP binary. So next page, please, Randy. Yeah, we already know how the FSP generally working, but if we look into the SM modules, we do see some problem. Firstly, let's take a quick look about the traditional UEFI way. This DXC and SM service was implemented in the format of DXC SM modules. These modules was dispatched in the DXC phase in the UEFI boot flow. And after this module was launched properly, the SM RAM environment was initialized and the SM handler was installed properly to satisfy the usage in the runtime phase. This solution works well for the UEFI flavor, but if we switch to other bootloader, the DXC and SM module cannot be seamless integrated intact. In this way, we do think we are thinking about the problem, and we realize that we want to have a unified redistributable SM module also to supporting the different bootloader to complete our open system firmware solution. Next page, please. Yeah. Then let's look into the RAS. RAS is a very important SMIP, and it's no doubt it is more and more important in the cloud environment. In the left side, we see a runtime RAS stack, the firmware and the OS working together to handle the RAS, to handle the hardware errors. When the hardware error happened, it will trigger SMI, and this SMI was processed in the SM by the RAS handler inside the SM execution environment, and also some runtime interface was existed to get OS also to follow to do further process to this hardware error. So this runtime RAS stack was set up through boot time. So when boot time, if we recall the previous page analysis, we do realize those SM modules was not available in FSP, and it's not by default enabled with FSP solution. So here we will looking to explore a solution to enable RAS within the FSP binary. Next page, please. Okay, so let's go to our solution. So how to, with existing FSP, how we, to enable runtime RAS, we have complete solution which include multiple components. The first component will be the RAS modules. Currently, it takes the format of the DXC and SM, and we will convert them into PIM and standalone SMM. And we will make sure our MM core to support launching these standalone MM modules. Intel will provide our RAS modules, but besides that, if there are some OEM modules, we will providing the late MM loader to load the OEM modules in later boot phase. Consider the needs for the SM module to be updated even in runtime. So we're also introducing the runtime update framework, which can receive the new MM modules in the runtime. For all the important 4 pieces, we will encapsulate all of them into FSP binary. Using existing FSP definition, we put it into FSPS section. And in this way, if we look to boot flow, we will see using Coreboot as example. So the Coreboot will using the existing FSP API to calling into the FSP binary. After memory got initialized, And the bootloader will call FSP silicon init to start the silicon initialization routines. And follow that, our standalone MM core got launched to start the to initialize the SM environment, the RAS modules, the MM loader, and the runtime framework will be continuously to be installed into our SM execution environment. Looking to the RAS handler itself, RAS functionality itself, besides the function inside the SM, there's also some interface need be proposed or routinely proposed to for runtime usage. So the our standalone our SM modules will also when it gets invoked, besides to install to the SM RAM, we're also providing some hub on demand to bootloader. So bootloader can pass this hub and publish the runtime service to OS per the RAS functionality definition. In this way, we will see the SM RAS handler was installed properly, and the runtime interface can also be provided after some change in the coreboot and provided to the OS for later call. Next page, please. So follow this technical proposal. We do a prototype, and we can choose the how our prototype works with the demo. We choose one RAS handler as an example. It is the address translation. This RAS handler has two-part functionality. Inside the SMM, there's SMM handler is installed to do the address forward and reverse translation. Also, this RAS functionality need another ACP, will expose an ACPI record for OS to call. So we choose this RAS handler for demo, and our prototype work covers we convert this module into a PIM and standalone and put it into FSP and get it to be work together with Coreboot. We will see the SM handler was installed in the SM environment, and ACPI table can be seen in the OS environment. So next page, please. Yeah, so this is a demo. We show that through our bootlog. So we already having, we built an image which includes the FSP binary, includes the Coreboot as bootloader, also put into the Linux boot as a payload into the FSP into the flash image. After press the power button, the system got boot. The first you can see in the FSP log, the SM handler got installed, and also a hub was actually exposed. And then if you look to the Coreboot log, we will see the hub was received. The Coreboot can see the hub, and then they will patch in the SSDG to including the address translation table. And this table can also be seen if you read the Linux boot log. The ACPI table is there as expectation. After booting our production OS, we use Ubuntu as our target OS. If you look to the ACPI table, the address translation handler was there as expectation. If we start a soft SMI to trigger this RAS handler, you will see the SM handler was invoked successfully as our expectation. So this is our quick demo to showcase our prototype work. And this is all for my presentation content. So going to the last page, call to action. Yeah, definitely. This is exploration to make sure we can have a good open system firmware solution. Yeah, please get involved to the open system firmware. Also, welcome to engage with Intel for the FSP development and also contributing to our open firmware development. Thanks. This is all. Thanks, Randy. So my talk is finished.
Thanks a lot, Ruth. Appreciate it. I think we ran out of time for Q&A. Thank you.
Thank you, Randy.
Thank
Thanks,
you.
everybody.